Good morning, friends. We'll continue with the continuity. We have discussed about continuity of a function at a point. Now we'll be discussing about the continuity of a function in a given interval or continuity of a function in its domain. A function f is said to be continuous if it is continuous at each point of its domain. Say if f is defined on a to b, for f to be continuous on AB, it has to be continuous in the open interval a to b, and the right hand limit at a should be equal to f of a, and the left hand limit at b should be equal to f of b. Then we say the function is continuous in the closed interval a to b. So in a very simple language, we should understand the function is continuous in its domain if it is continuous at each point of its domain. We'll see an example. How do we check the continuity or examine the continuity of a function? The example is function is f of x, 3x minus 2 for x less than equal to 1 and 3x minus 4 for x more than 1. Now the question is it a continuous function? We need to justify. So first of all, whenever we have a function, just identify its domain. We have the domain of this function is all real number. This function is defined for all the real number. Now we'll be taking an arbitrary point from the domain. So let's C belongs to R, any real number. Now we'll be having the cases. What are the cases? First case is when C is less than 1. If it is less than 1, so we know the function for less than 1, it is 3x minus 2. So we can write f of C is equal to 3c minus 2. Now we'll be taking the limit of this function. So limit x tends to c f of x is limit x tends to c, and for this function we have the function as 3x minus 2, so we'll replace f of x by 3x minus 2. So we are having as 3c minus 2. So we find that it is equal to f of c. So we can say it means we have got the limit equal to the value of the function. So we will say it is continuous for all c less than 1. Now case 2, when c is greater than 1, then we take the function for greater than 1 as 3x minus 4. So we can write this f of c as 3c minus 4. Again we will be taking the limit of this function at this point. So limit x tends to c f of x, we can write limit x tends to c 3x minus 4, and substitute the value, we are getting 3c minus 4, which is equal to f of c. So we can say that it is continuous for all c greater than 1. Now the third case is if c is equal to 1. If c is equal to 1, again we have the functions for equal to, it is again 3x minus 2. So we'll write here now f of 1 as 3 into 1 minus 2, that is equal to 1. Now the limit, left hand limit x tends to 1 minus f of x. Limit x tends to 1 minus, will directly take the function because it is defined for less than 1. Now again substitute the value, we are getting 1. Right hand limit is limit x tends to 1 plus, and it is 3x minus 4. The function is defined for right hand as 3x minus 4. Substitute the value of x as 1. We are getting it as minus 1. We find that it is not equal to f of 1. So what we can conclude now, that it has a discontinuity at x is equal to 1. For all other points the function is continuous, and it is thus discontinuous at x is equal to 1. Now another example, prove that f of x sin x by x, x less than 0, x plus 1, x more than equal to 0 is continuous. Again the domain of this function is all real number. let's say be any real number. So the cases we have as earlier, less than 0. So f of c for less than 0, f of c is what? Less than 0 sin x by x. So f of c will be sin c by c. Now we'll be taking the limit x tends to c. So x tends to c. So put the value, substitute for x as c, we are getting sin c by c, which is equal to f of c. So we can say it is continuous. Again, for more than 0, we are having that f of c. It is defined at x plus 1, so we'll write it as c plus 1. For limit x tends to c, we can write it, substitute the value of the function x plus 1, and again replacing x by c, we are getting c plus 1, which is equal to f of c. So we can say it is continuous for all c greater than 0. Now at c is equal to 0, c is equal to 0, f of 0 is, you are getting 1. Left hand limit x tends to 0 sin x by x is 1. Right hand limit, again we are getting 1. We find the left hand limit, right hand limit, they are equal, so limit exists and it is equal to 1, which is equal to f of 0. So we say that f is continuous at x is equal to 0. On combining all the cases above, it follows that f is continuous at all c, or we can say all x belongs to R. Now we'll be discussing about algebra of continuous function, or we can say the properties. If f and g be two real functions continuous at x is equal to 1, let alpha be any real number, then these are the properties we have. Means sum, difference, continuous at x is equal to a, alpha times of f is continuous at x is equal to a, f into g is continuous at x is equal to a, f by g is continuous at x is equal to a, provided g of a is not equal to 0. 1 by f is continuous at x is equal to a, provided f of a is not equal to 0. We'll just give you one proof, remaining all you can do it by yourself. Limit x tends to a, f of x is equal to f of a, and limit x tends to a, g of x is equal to g of a. Why? Because they are continuous functions, so the limit exists and they are equal to value of the function. Now we are going to find out the limit x tends to a, f plus g of x. So f plus g of x from the addition of two functions can be written as f of x plus g of x. And from algebra of the limits, we can write this as limit x tends to a, f of x plus limit x tends to a, g of x. And since limit x tends to a, f of x is f of a, limit x tends to a, g of x is g of a, so we are getting it as f plus g of a. So now we can write this as f plus g of a. So we have got the limit of the function is equal to value of the function at that point, so we can say f plus g is continuous. On the same line, we can have the proof of all other properties, so we should understand that these properties are all valid one. Now one theorem is there that let f and g be real functions, that's that the composition f of g is defined if g is continuous at x is equal to a and f is continuous at g is equal to a, g of a, then f of g is continuous at x is equal to a. Now we'll see the proof. F of g is defined. It tells you that range of g is a subset of domain of f. It implies that g of x all belongs to domain of f. Now g is continuous at x is equal to a, so we can write limit x tends to a, g of x is equal to g of a. And f is continuous at this point, so we can also write that limit g of x tends to g of a, because g of x is an element from in the domain of f, so it tends to g of a is f of g of x is equal to f of g of a. Now g of x tends to g of a, so when x tends to a, then g of x tends to g of a, so we can replace g of x tends to g of a as x tends to a, and we can write the function as it is. So f of g of x is what? F of g, and f of g of a can be written as f of g. So what we find, that limit extends to a of the function is equal to value of the function. So we can say that this composition f of g is continuous at x is equal to a. So we have understood that the composition of two continuous function is also continuous at that point. Now some properties. Properties are that these proofs, it is already given in your book, some of the proofs, and they are very easy. So I'm not going with the proof. I will just enumerate all these properties. First is a constant function, identity function, polynomial function, modulus function, exponential function. They are all continuous everywhere in its domain because their domains are the real numbers. Again, the rational function is continuous at every point in its domain, provided its denominator is not 0. Logarithm function is again continuous at every point in its domain. Sine and cosine function in the trigonometry, they are continuous everywhere because their domains are again all real number. Tan, cot, sec, cosec, they are continuous in their domains. All inverse trigonometric functions continuous in their respective domains. So these all are the functions for which we know they are continuous in their domains. Now, one example here, examine sine of mod x for continuity. Means we want to check the continuity of this function. So what this is, we know there are two functions here. One is the sine function and other is the mod function. Outer function is sine function, inner function is mod functions. So accordingly, what we need to do first, identify the outer and inner function and then assume let f of x is equal to f mod x and g of x is equal to sine of x. So here the outer function is g of x, inner function is f of x. So if we find g of x, so we can write g of f of x, put the value of f of x as mod x. Now g of x, so we'll replace in the g of x by mod x. So we are getting sine of mod x. So we have got that this function is the composition of two functions. One is the mod function, other is the sine function. Now we'll take the help of the property. F is a modulus function continuous everywhere, and g is a sine function continuous everywhere. And the given function g of f, composition of two continuous function. So we know that composition of two continuous function is continuous for everywhere. So we can say this sine of mod of x, it is nothing but g of gof of x. So it is also continuous. So whenever you have the composition of functions, and if you know that its constituent functions are continuous, so we can say that the composition of two continuous functions are continuous. Thank you very much.